హలో. Vaishnavi, are you there, ma?
Yes, ma'am. I'm in.
Hello.
Yes, ma'am. I'm there, ma'am.
Hello.
Ma'am, yes, ma'am.
Okay, ma'am. Palani, shall we start, sir?
Yes, Professor, we can start.
Yes, sir. 1 minute, sir. A warm morning to all the participants. Hello. Is my voice audible?
Yes, ma'am.
Yes, Professor.
A warm morning to all the participants, guests, and research scholars. On behalf of Triple Department, we welcome you all for our AICTE-sponsored STTP Phase 3, Recent Trends in Renewable Photovoltaic Systems and its Research Challenges. For the last day, we have two sessions. For the morning session, we have Dr. Palani Swami, sir, who is going to discuss on the topic Challenges in Renewable Source Integration. And for the afternoon session, we have Dr. Vikram Kulkarni, sir, who is going to discuss on smart grid automation. So now I request Vaishnavi to open the session.
A very good morning to one and all. Firstly, I would like to give my grand welcome to all on behalf of Sri Venkateshwara College of Engineering, Tirupati, Triple Department. As with all your cooperation and patience, the 5 days of this faculty development program, sponsored by AICT 1 week short-term training program on research trends in renewable photovoltaic system and its research challenges phase 3, completed successfully. And today is the last day of this faculty development program. I would look forward to you having a pleasant stay and a nice learning experience here. With these words, once again, I welcome you all. So, before going to start the session, some instructions to follow as all the participants are requested to mute your microphones and turn off your cameras, and also suggested to pin the resource person screen. As I'm very happy for having this opportunity to welcome such a noted personality, none other than Dr. Sudhir Kumar sir, Head of the Department Triple SVC. Welcome, sir. And now I feel grateful to welcome our resource person, Dr. K. Palanswamy, presently working as Associate Professor in the School of Electrical Engineering of VIT University. He has 6 years of teaching experience. Sir has completed BE at KSR College of Technology and did his ME at Coimbatore Institute of Technology, and also completed PhD in Power Quality Improvement at VIT University. He published 51 international journals, attended 18 international conferences, and also 8 national conferences. He published 7 book chapters in reputed publications and also edited 1 book. Sir has completed various consultancy works on power quality monitoring. He is also a member of IEEE, IET, SEEM. In his professional career, he worked as head Energy and Power Electronics in School of Electric Engineering and VIT University from 2016 to 2018. As Sir is also a University Energy Audit Committee member. His area of interest are low inertia power grid, smart grid, and also power quality improvement and some other too. And now I request Dr. K. Palanswamy sir to take up the session. Welcome, sir. Sir, I request you to welcome.
Yes, yes. Thank you, Vaishnavi and other professor. Just I will share my PPT. I hope my slide is visible, right? Can you all see my slide?
Yes, sir.
Can anyone respond? Can you all see my slide, PPT?
Yes, sir, it is visible, sir.
Yeah, thank you. Okay. Thank you very much for the nice introduction, and thank you, Dr. Sudhir and Dr. Lakshmi ma'am, and other deans and directors.
Thank you, sir.
The talk is on challenges in renewable energy source integration. Before starting this, I'm going to express some of my research ideas and contributions. So before that, let us try to understand, why are these things, like the discussion. What are the challenges mainly and why it is so, right? In general, when you say renewable energy source, the major contribution is from solar and wind, right? So, and the solar and wind are highly random, right? Highly intermittent in nature. Oh, okay. So, when you take solar, it rises from early morning, like 6 a.m., and it reaches its peak value somewhere around 11 and still stay at peak value or near peak value around 2 p.m. And after that, it will try to, it will fall, then reach zero at 6 p.m., right? So that is how, we used to hear or we are, taught. Okay. So, we used to see something like this, right? This is peak periods, maybe 11 to 2, and this is 6 a.m. and this is 6 p.m., right? So this is how, like, we can say power generated, okay? And this is time, T, okay? This is especially for solar. So this is how we are taught in our schools and colleges and, even in our research program. But actually it is not so, right? We may not get a smooth characteristics like this, right, in terms of or from the solar. And also, when you take wind, normally wind and solar, complement, we can say complement to each other. Even if it is not so also, right? For example, if you start again, 6 a.m. to 6 p.m. and so on, right? Let's say this is 6 a.m. and so on, right? See, during night, right, it may be good, and even in the early morning, it will be somewhat good, and will reach to its low value somewhere around 10 or 11 a.m. and it may stay, it may vary, right? Around 4 or 5, again it will get peak, right? Something like this. To its maximum value, it will go, right? So all the day it may not be so. It may have some other characteristics also, but still, in general, I can say during the peak months, right? That is somewhere around. See, the wind may start somewhere in May, right? May or March in some places. So it may start from May or March and it will go till October, right? So only for those 6 or 7 months you will get very good wind, right? In all other times you may not get wind, especially in Tamil Nadu, in our wind pass areas. Our characteristics is like this. Start somewhere around mid of March or April or even May, and it will peak, go to peak somewhere around June, July, and August, September, October. It may little fall, but it will exist till October, right? This is how it will, give the wind, good wind velocity in the wind passes. Right? But again, though it is seasonal, right? The wind is seasonal, but in between the day, right, or within a day, also it will vary in a very highly random way, right? That is what all about the problem, right? The solar, we are thinking like a pure, half-wave sinusoidal waveform, but it is not so in practical. And wind will be, a complement of this solar. That is why, when you integrate solar and wind, you will get a almost constant power, the full day, right? Or, entire, what is it? Years, right? So that's how we used to think, right? But though it is like this, but in between, right, if you take a small time step, then it will not be very constant or very a similar characteristic like this, but it will have a lot of ups and downs, right? So what I mean to say is like this. So within a day, it will vary like this, right? And like a harmonics in the power waveform. Something like this, right? It will not be a constant or smooth waveform, something like this. Okay, right. So what I'm trying to say is, since the solar and wind are highly varying within a day, within an hour, or within short time, right? Though we have a solar and wind, maybe as a captive power plant or as a big industry, you can have your own big solar plant or big windmill. But still, you may need this diesel generator backup, right? So you may need a diesel generator backup. So what will happen normally, if you are relying only on the solar and wind, right? You may need, for example, if you have a 1 megawatt load, I'm just telling you example, right? 1 megawatt of load, and you have more than 1 megawatt of solar or more than 1 megawatt of wind, or combined together, maybe around 1.5 megawatt, something like that, right? So still, even if you have 1.5 megawatt of combination of solar and wind, you may not be able to supply this 1 megawatt constantly to the load, right? So that's why we need a diesel generator backup, right? When good sunshine and good wind blow, then you may get more than 1 megawatt also. Of course, you cannot have a storage because that is very costly. Even if you plan, it is very optimized size. It cannot be for the full 1 megawatt or to meet the entire power from the solar and wind, right? That's very difficult. Okay, so you may need to run a diesel generator. So if your load is 1 megawatt, the diesel generator backup, it means I can say a hot reserve, spinning reserve, will be somewhere around at least 70%, right? So maybe 0.8 MVA or 0.8 megawatt, close to that, you have a spinning reserve. So you have invested a lot to solar and wind or other renewables, but still to meet the 1 megawatt load, we are having 0.8 MVA of diesel generator that is continuously running, right? So 0.8 megawatt or 0.8 MVA diesel generator may not supply good power or good percentage of load all the time. It may be even it go to like 10%. It may supply for some interval, and the supply may be reaching 100% in some interval where you do not have this good sunshine or the wind speed which is less than cut-in speed, right? So all those things will cause the load variation between 10 to 100%. And you must understand the generator, any generator, okay, the efficiency characteristic is something like this, right? So it will give a peak value somewhere around 80% or 88 or 90%. It depends on the system, but mostly the peak is less than 100, right? The peak efficiency point is less than 100. Okay, right. What I'm trying to say is, when you operate only at least 80%, 75% of your rating, then you will get a good efficiency, right? This is a load factor, right? Output, okay, and this is efficiency. So only when you run around 80%, maybe 70 to 90% load, then you will get a good efficiency. But most of the time, your diesel generator may run like this, right? You are burning up, diesel, but it is operating at very low efficiency, right? It is not even 30%, 40%, something like that. So it's all, you are not only, wasting the fuel, you're also, during low load, the carbon dioxide emission also will be good, considerably high when compared to when it is operating at high efficiency or good efficiency, right? So all these factors, right, you need to consider when you say the renewable are highly random. So it's connected with all these points, right? Okay. The other side of the grid operator is actually the grid operator will expect a constant that's called firm power, so that he can manage the grid operation. It means he can balance the demand and generation, right? Okay. So when I say constant power, some of you may misunderstood or misinterpret constant power for a particular period. For example, if the load interval or the schedule interval is 15 minutes or 2 15 minutes, combined is 30 minutes, right? So 15 or 30 minutes or 10 minutes interval, you should ensure a constant power supply, right, from your generating facility, right? So that is why, earlier, right, in some of the developed countries, that is restructured power system also, right, or the what is it, advanced power system, or you can say automated transmission and distribution systems, right? There normally you have to schedule your generation. For example, if I'm running a solar PV or wind, right, I must give the schedule at least one day ahead, right? Maybe for tomorrow's power generation or power schedule, I have to give today at least 24 hours before, right? It is something like, for example, if I'm a solar producer, see, let us say I'm again 6 a.m. to 24. Okay, so this is actually again 6 p.m. Okay, right. See here, my generation will be something like this. Generation schedule, like a multi-level inverter, output. Okay. Something like this. So for every demand or the generation interval, this can be 10 minutes in some countries, 15 minutes or 30 minutes, right? This each interval can be 10 minutes or 15 minutes or 30 minutes, right? So during that time, I should fix, yes, I'm going to give 800 kVA, right? 800 kilowatt, right? Or 5 megawatt. I must give the schedule, right? So between 11 a.m. to 2 p.m. I have a source of 2 megawatt, let us say. So I can give 1.6 megawatt, right? During 11 a.m. to 2 p.m. I can give 1.6 megawatt. So accordingly I will schedule. Okay, right. Now the question is, even Central Electricity Authority (CEA) is permitting to the forecasting people or forecasting research group, right? You can have the variation of plus or minus 15%. In India, CEA gives the guideline of plus or minus 15% variation is allowed. For example, if you have committed 1 megawatt of solar or wind power, you can vary 850 kVA to 1.15 megawatt. You will not be penalized for that variation, right? If you have committed 1 megawatt from your solar or wind, you can either supply or you can supply between 1.15 megawatt to 0.85 megawatt. So within that range, if you vary, the grid operator should not penalize you, right? But if the variation is beyond, for example, I have committed 1 megawatt, but I should not supply, for example, 1.2 megawatt or 1.3 megawatt. Even for supplying at the higher side is also penalized, right? Similarly, if I committed 1 megawatt, I cannot go less than 0.85 megawatt, right? So if I go less than 0.85 megawatt, I have to penalize, or I have to pay the penalty, or my the generation, the bill will be reduced. Okay, right. So this is what the strict, what is it? The agreement between the seller and the grid operator, or the system operator. Okay, seller should commit X amount of power, and he will be allowed, or he may be allowed to vary plus or minus 15% from the X megawatt or kilowatt, right? Beyond that, if we reach or if we go, then he will be he has to pay the penalty. Okay, right. So what you have to understand, to meet the, see, for example, if every seller, it means the individual power producer is committing like this, the grid operator or system operator will consolidate everything and he will manage. For example, if similar way, the load scheduling also, the big customer, the industrialist, right, should commit, okay, so and so hours, what will be the power consumption from my industry? Something that he has to commit, right? If he go beyond that or less than that, then he will be or he need to pay the penalty. Okay, right. So he will, the system operator will aggregate the generation, like this. If there are 100 sellers, from all the 100 sellers, he will consolidate, aggregate this. Similarly, if he is having like 200 consumer, it means load, he will consolidate the load scheduling from the individual customer. So you will aggregate. So you will try to balance. For example, if particular instant generation is greater than the load, he will try to sell to the cross border. For example, if it is a state electricity board, then he will start to sell the power, or he will start to commit the power of selling to the nearby state. Maybe Tamil Nadu can sell the power to Andhra Pradesh, or Andhra Pradesh can sell the power to Tamil Nadu or Kerala, something like that, right? So the cross-border selling he can plan if he know the aggregation of generation scheduling and aggregation of load selling, right? Okay. So at any instant he has to maintain, strictly follow this. If he is not following, then the frequency will start to vary, and that will create a lot of issues, because most of the protection relays are frequency change based operation, right? So when the frequency changes beyond its threshold level, then it will get tripped, over frequency as well as under frequency. So to ensure that it is to balance everything, the grid operator will plan. He may buy the power from cross border or other supply service provider, or he may sell the excess power which is available from the aggregated data to the nearby state or cross border service provider. Okay, that is one thing. So that is the second point you must understand. So the highly random nature of solar or wind is not only hurting the immediate user, it means who is owning the power plant, but also to the electricity board, it means service provider or utility, because he is handling thousands of such variations from thousands of customers. Okay, so that also you need to take care, right? See, this is what the job is done by the regional load dispatch center, SRLDC, that's something like, right, load dispatch centers. Okay, right. So you are very good, knowledgeable, and the optimization experts are sitting in the LDC, it means load dispatch center, or regional load dispatch centers, and they will plan accordingly, right? The power exchange, all those things actually are operating based on this one. Okay, now I just want to say show some real-time experience, right? So that you will you will appreciate me, right? See, this is one of my university plant. See, recently we have installed 1 megawatt of solar PV. Dear professors or researchers, can you see the internet page? Can anyone respond? Hello. Can anyone respond? Can you all see my, the internet page? Oh, nobody is with me. Madam Lakshmi ma'am, can you hear me?
Yes sir, yes sir.
Oh, okay, great. Ma'am, can you see the the internet page?
Yes sir, it is visible, sir.
Okay, thank you. Okay, see, this is what I want to show to you all. See here, this is our the online energy monitoring platform. This is supplied by one of the vendor. Okay, so we have 1 megawatt solar plant. You can see this is 1 megawatt, right? 1 megawatt of solar plant we have. Of course, we have 2 megawatt, but this 1 megawatt is from other suppliers, so that's why we have a separate page for this. Okay, can you see this red mark and green, then blue, and so on? See, this is the first page of our entire plant, and you can here in some of the in some of the places you can see the red mark, right? And the reason or the indication is actually fault. See, today is the maintenance shutdown for our campus. It means we don't have any EV power supply today from 9 a.m. to 6 p.m. See, we need the power of somewhere around 4 megawatt, right? 2 to 4 megawatt is the entire variation. Okay, but this is just 1 megawatt. But even for this 1 megawatt, our people are not able to handle the variation of the solar plant. See, we are running the diesel generator from all our powerhouses. We have around 10 powerhouses within our campus, right? It means 11 kV bar, 415 substations. We have around 10 numbers, and of course we have one high tension line, that is 33 bar 11 kV. So all the 10 powerhouses, they are running the generator, and they are, unfortunately they are not able to manage the variation of the solar. So what they have done, they have, they what is it? Switched off the solar. You can see the first page, 2 inverters are switched off, and the second page also MGR block is not working. In third block, 2 inverters are switched off. Fourth page, of course, not, something like that, right? So out of 1 megawatt, and see, can you see this blue color curve? See, this is the the power generation curve, and you can see it started somewhere around 6 or 5:45 a.m. and see how it is varying, right? It is varying like this. It's not as you see like in the sinusoidal waveform or half wave sinusoidal, right? It is varying like this, and see around this time 10:30, it almost came down to very low value, right? So all those things, right, you are supposed to handle. Okay, right? So these are the unexpected, or you can say untold truth by the solar manufacturer or the wind manufacturer. See, they will sell that, or they will, for the sake of selling their product, they may say all the things, but internally these are the things that are happening. Okay, right? And the next thing is, see, in some grid connector or grid what is it, inverters, right? Based on the generation or based on the need, it may connect or disconnect from the supply, right? So during the synchronization and resynchronization, right, it means it may connect anytime it wants, and similarly it can disconnect when it finds some problem with the grid or something like that, right? It will disconnect. So during that time, see, the grid configuration, see, you are going to connect an inverter parallel to the grid, right? Like that, there may be n number of inverters connected, synchronous generators connected, and many other loads are there, right? So when random numbers of the solar PV stations or diesel generators or load, if comes and goes out of the station, what is happening? Indirectly, the grid impedance is highly dynamic or highly varying. So the proper operation of let's say shunt active filter or the variable frequency drive, even active power factor correction devices, or the other solar panels, solar inverters needs a street, or you can say almost a constant or a small bandwidth of the grid impedance. See, of course, most of you must have studied or experienced the LCL filter. Nowadays the solar PV or active power filter or any VFD or anything is coming with LCL filter, right? So the LC, of course, we all know to suppress the switching frequency, switching frequency, there will be a switching signal to reduce that switching impact to the weak or reasonably strong grade. What they will do, they will try to reduce the switching impact by connecting the LC filter. Okay, that is very common. Of course, we have studied in our power electronics and everywhere, right? But the recent technology is LCL filter. The LCL filter is actually, the LC is our side, the other L is from the grid side, right? When the grid impedance is highly dynamic or highly varying because of the configuration, because of the n numbers of solar PV inverters are connected, disconnected, many things, right, at instant to instant. So because of that, the third L, it means LCL, that L is highly varying. So if that is varying, your active power filter or your VFD or your solar inverters will not, maintain its, good power quality to the grid, right? So that is also will be an additional burden to the grid. Okay, right. And the fourth thing is actually contribution of active reactive power techniques. It is something like, for example, I have 1 megawatt solar plant. Maybe the other person may have, 500 kilowatt of solar plant. Maybe some X and Y will have 5 megawatt, 10 megawatt, something like that, right? See, when there's a frequency event, when I say frequency event, the frequency can go up or can come down based on the balancing of generation and demand, right? So when the frequency varies in the grid, what will happen? The conventional synchronous generator, of course, it is having kinetic energy because it is having huge rotating mass. So from that it will manage. But the grid connected, the inverter, power electronics based inverters may not have an inertia. So what we have to do, by adjusting our active power injection, right? We strictly talk about active power. By adjusting the active power, I can help the frequency regulation of the grid, of the microgrid, right? For example, if the frequency is increasing from 50 Hz to maybe 50.05 or 50.1 or so on, right? So what I can do, I can start to decrease the active power injection to the grid. By applying MPPT or some other technique, I can try to reduce the the active power injection. Similarly, if the frequency is falling down from from 50, it can come to 49.95 or 49.9, something like that. What I will do, by having a short time backup, what I will do, I will try to increase my active power injection. This is called inertia. By following the frequency of the grid, I can increase or decrease the active power injection, right? Of course, I need to have energy storage, proper energy storage, or I need to have a proper mechanism so that only then I can have the frequency regulation support. Okay. What about the reactive power? See, unlike frequency, of course, frequency is constant throughout the grid. Whether you are measuring here or at Andhra Pradesh or Maharashtra, the frequency is constant if the grid is interconnected, right? But voltage is not so. See, when I measure the voltage here, within my campus, maybe if I measure in a main building, it may be different value, and if it goes to other building, right, maybe 1/2 kilometer or 1 kilometer away, that will have a different voltage. So voltage is not a global variable. So if at all my inverter is working, let us say right through. For example, if the grid is facing voltage issue, low voltage or over voltage, what I will do, being a active power device or active converter, what I will do, I will regulate, or I can regulate the voltage, system voltage by adjusting the reactive power. If I measure or if I feel the voltage is greater than the rated voltage, nominal voltage, what I will do, I will start to absorb the reactive power. Of course, I should not, but the recent grid code says you have to, right? You have to support the right through for the grid voltage or voltage support, right? So whenever the voltage goes beyond it means higher side, beyond the rated voltage, then I have to absorb the reactive power. Sir, see, you must understand, if you have designed 1 megawatt of solar PV inverter, when it is supplying, let us say, 10% of the reactive power, accordingly, the active power must be reduced. Because at any instant or for a longer interval, you cannot have overloaded or overloading of your inverter. So when I am injecting the reactive power or when I am absorbing the reactive power from the grid, accordingly my active power must be reduced. So I am losing the profit. So all those things are there, when you are operating with the grid connected, right? So the the quantum or the amount of active or reactive power supplied to the grid, right, or absorbed from the grid is based on the rating of your device, the rating of your plant. It means if you have 1 megawatt, based on the frequency up or low or voltage high or low, you may be allowed to have 10%, 15%, right? So that kind of command you will get it from the the microgrid central or master operator. So in microgrid operation also that will be an issue. For example, if the microgrid is a wide area, for example, a few kilometers square, so it is very difficult to follow, track the command from the central microgrid operator. So that is why most of the the power converters or the renewable energy converters, what they will do, based on the local variable, it will derive the control parameters. I repeat, most of the power converters, let it be solar converter or wind or whatever the renewable converters, power converters, will derive the control parameter, control variable, right, from the local variable. What are the local variables? That is your voltage and frequency, right? When the frequency goes up, as I told you, I will reduce my active power injection. When the frequency comes down, I will increase the active power injection. Similarly for the voltage, if the voltage goes high, of course, as I told you, the voltage is not a global variable. So based on the measurement point, the voltage will vary. So definitely for injection or absorptions of reactive power should be taken locally, right? Based on the local situation only, you have to take the decision, right? So your power converter must be intelligent enough to calculate or to derive the control variable based on the variables of the grid, that is frequency and voltage, right? Then nowadays, because of the Pesar measurement unit or time-stamped values of the grid parameters, right? Recently, people are talking about delta. It means delta, or you can say power angle. Okay. See, based on the power, or sorry, phase shift also, you have to understand certain things actually, right? You must understand the Pesar measurement unit is actually measuring the magnitude, also the phase, right? So if I measure the voltage and its phase in 3 or 4 different places of same microgrid, that phase angle will communicate lot or will convey lot of things to a lot of insight to the grid operator. See, for example, we have 4 corners, like let us say it's a 5 or 10 kilometer squared microgrid, and let us say it is like a rectangle, for a simplicity, right? From all the 4 corners, I am measuring the voltage. Let us assume, the northeast that is giving the voltage. Of course, the voltage magnitude can vary, plus or minus 5%, but the phase angle is enormously, or you can say alarmingly high or different from the, the other 3 corners of the power system. I repeat, let us say it's a rectangular, area of power distribution. I'm measuring the voltages from all the 4 corners, right? And in one particular interval, the northeast measurement is giving, as I told you, plus or minus 5% voltage variation is okay, but the phase angle, when compared to other 3 corners, is alarmingly high, or it is very high, it's deviating much. So I must understand there is going to be some issue, close to the northeast corner. So what I will do, I will, reconfigure the power system in such a way. Maybe I will disconnect the northeast feeder, or I will, send an appropriate signal to the source who are sitting near to the northeast corner, and I will, support, I will help the system to ride through, right? All those things should be done. That's the kind of, Pesar measurement unit signal, right? So when you see the variation of Pesar, right? So you must take appropriate action and issue the command signal or commands or signal to the individual operators or individual small operators. Okay. Then, so we have discussed highly random and grid operator requires constant power. Sync and resync is always an issue to the other power converters which are connected to the same grid. Then contribution of active reactive power based on the ratings, right? So all those things is to support the grid, right? So the extension of that is energy storage. Nowadays, when you have more and more renewable energy source contribution to the microgrid or grid, you have to be very careful, or you have to be or you should have a reasonably good size of the energy storage battery or any kind, right? The battery also can be flow battery or any lithium ion, NAS, sodium sulfur, right? It can be any battery, and need not be always electrochemical. You can have the compressed air energy storage. Of course, it is not mature technology in India, at least I can say. In other part of the country, yes, other part of the world it is fine, but in India we are not using much of the compressed air energy storage, right? So it can be pumped hydro, or it can be the flywheel or supermagnetic energy storage. So at least your energy storage system you must have in your what is it, flywheel, right? So you must have in your system so that we can manage the variation of power generation and load, right? So we are going to see what are the different kind of energy storage in the coming slide. And see, interaction between active devices. See, here the DG is distributed generation. So I have a lot of what is it, case studies, right, from the industry. See, when you buy a active power filter to take care of some 5th and 7th harmonics or some other harmonics, and also to supply reactive power, normally you should give the proper information to the supplier, right? The APF active power filter supplier, because when we have more, for example, more VFDs, variable frequency drive, right? That too, 6-pulse rectifier based VFDs. So 6-pulse rectifiers definitely will have a characteristic harmonics of 5th and 7th, right? In my grid or in my power system, I may be having more 5th and 7th harmonics because my VFD front end is actually 6-pulse rectifier. Or I can have, to some good extent, I can go a 12-pulse rectifier, 24-pulse rectifier. So based on the number of pulse, I may have different, the characteristic harmonic. So if I'm not, or if the system provider, that means active power filter provider, if he is not measuring it properly to my system, if he supplies something else, right, it may not operate properly with our system or with my system condition. Because see, when you are bringing active power filter parallel to the other loads, right, of course to the grid, right, the grid impedance will vary, right? Because see, there is a source, let us say the entire grid as a source, and parallel to the source we are bringing the active power filter. So what will happen? There will be a combination of source impedance and the active power filter impedance. So what will happen? The VFDs or active power filter correction capacitors or the other solar inverters which are connected in the same system will start to behave differently, because to the point, it means still you are not connecting the APF, active power filter, your grid impedance is different. The impedance seen, source impedance seen by the VFD or source impedance seen solar inverter may be different, but you are connecting all of a sudden as active power filter, so the grid impedance will vary. That dynamics, right, if you are not taking it, you are not taking care of it in a proper way, so it will lead to other issues. So the solar inverters will start to inject a higher order harmonics. Similarly, variable frequency drives will start to inject higher order harmonics, because see, you are connecting something parallel to the source, so the system impedance came down, especially for higher order harmonics. So your characteristics will change, right? So all those things you need to take care when you are going for solar PV or the wind or any other things actually, right? Then see, though we are talking about, yes, we have to go more and more green. We should save our world, our environment by reducing the carbon dioxide emission and so on, right? Many things we are talking, but still, the private parties are little afraid. The private power producers are little afraid of this, the market clearing price. See, for this also, I will take you to a real-time example. See, I will show you a site where you will get some idea of this one, right? I don't know how many of you have experienced this kind of website. Can anyone tell me in our group, right? I'll see how many are there in the group. Now there are 29 people are attending this course, right? Out of 29, how many people have visited this kind of website? Indian Energy Exchange. This is one such site. Of course, there are many, sites or many power exchange platforms are there. So how many of you have seen this one? Can anyone reply? Have you ever seen this kind of site? Again, nobody is answering, right? Okay. Let's look at
Sir.
this. Yes, ma'am.
Hello.
Yes, ma'am. Yes, ma'am. Okay, fine. You are listening. Fine. See, average MCP, average market clearing price, peak MCP, non-peak MCP, max MCP, minimum MCP, right? And this is actually 3 rupees per kilowatt hour, 3.19 per kilowatt hour. Maximum market clearing price is 5.25 rupees per kilowatt hour. All these things actually, it is a platform where many sellers and many buyers are connected together, right? Of course, this is governed by Central Electricity Regulatory Commission and other Ministry of Power, and many people are involved in this one. So they are combining, they are giving the access to the seller. They are actually creating meeting point to the seller and buyer, right? So from this, you can just register and start to sell the price, so sell the power, right, from your renewable. It can be solar or non-solar, anything, right? And see here, this is actually the area price. It means you select your region and you can see what is the market clearing price, right? So maybe if time permits, if you are doing research in this one, maybe you can see this kind of website, iexindia.com, right? Where you will get the instantaneous market clearing price, right? And what is the quantum of market it is dealing, right? How much of megawatt solar, non-solar power is underselling or buying, right? Something like that. Okay. Now I'm going to show you a different point. The terminology called landed cost calculator, right? I'll just select it and I'll show you. See, this is actually DAM price is something like day ahead market, right? It means tomorrow by 11 a.m., by 12 a.m. What will be the MCP, right? All those things you can see here, right? We are talking about landed cost, right? Landed cost is something like, though you are buying the power from open access, I repeat, though you are buying the power from the from the open access with the price of 3 rupees or 3.19 or 2.9 rupees per kilowatt, still some other costs are involved, right? For that, see, I'm going to buy some power, so I'm choosing buyer, and my state is, sorry, though you are from Andhra or Telangana, I'm selecting this Tamil Nadu, sorry to choosing this, so Tamil Nadu, and my university, we are seeing the voltage at 33 as well as 110, so let me select 110 kV, right? This is kilovolt, right? Voltage level 110 kilovolt, okay, right? Let us assume I need 4 megawatt of power, right? And I need all the 24 hours, right? The power. And let us assume I am buying the power of 2.9 rupees per kilowatt, right? Now, if I give all this information, it means I am a buyer, I am from Tamil Nadu, my voltage level is 110 kV, from where I am getting the supply, and how much power I need, all the 24 hours I may need constantly 4 megawatt, right? I have given throughout the day, and my buying price, it means from the open access I am getting the power for 2.9 rupees per unit per kilowatt hour, right? See here, this is the tragedy. Though I am buying the power for the cost of 2.9, but when it comes to my premise, or when it comes to my point, my consumption point, I need to pay 5.28 rupees per kilowatt. Is there anyone to ask, or is there anyone to get some more clarification from this? Just look at this page. So I'm buying the power 2.9 from the seller directly from the open access market, but when it comes to my point of common coupling, I'm supposed to pay this 5.28 rupees, right? So my question is there anyone want to know something more than this, so that we will discuss more? Nobody? Great. Okay, we'll proceed. Of course, it is my responsibility to explain. See, there's a power system charge and state, cross state or cross border buying. For that, I need to pay some price. Then distribution. Of course, I am not paying anything to my state electricity board, because I am connected to the state electricity board already, and I am paying per kilowatt hour maximum demand price, right? So I need not pay this cross subsidy charge. And see here, all these charges, IEX transaction charge per unit, I need to pay at least 2 paise. And renewable power obligation charges. If solar is for 0.07, non-solar, it is wind and any other plant power, it is 0.1, right? Other charges are 0.02. So commissioning and many things are coming, right? So finally, it is coming to 5.28 rupees, right? So when you are contacting the the brokers, right? They will not say all these things. They will say, see, I can give the power for the cost of 2.5 rupees, 3 rupees. Only that much they will say. But finally, when it is landed to your place, you are supposed to pay this much. All these things are, the hidden agenda. Okay, right. Anyway, that's what about all these things actually, right? And grid codes are adjusted. Right. Definitely, I need to spend some time here. See, maybe before this grid code, let us say 2003 or before that, even till 2014 also, right? Certain grid codes are very stringent. It means, say you are connected to a grid, right? And you will be given certain regulations, like your device should not supply more than this much of harmonic level. You should not draw more than this much of reactive power because it's spoiling the entire transmission and distribution system and many things like that, right? And SACs, well, everything there are some definition by the IEEE, and that is what followed by most of the grids, right? So whether it is a Indian grid or any European grid, mostly they are following IEEE course, close to that. Okay. What I'm trying to say is, because of more and more renewable penetration, for example, when the renewables are start to exceed 30%, so it means 70% from the conventional resource, that means your synchronous generator which are operating at thermal power plant or any nuclear power plant, something like that, and let us assume 30% and more is our renewable contribution. So that time, earlier the voltage was plus or minus 5%. Now it is increased. How much it is? It depends on the grid code, right? Even it is increased plus plus or minus 2%, right? 5 plus 2 or 5 minus 2, something like that, right? Also, earlier the frequency change is plus or minus again 5%, right? 2%. This is also increased, right, to the higher side as well as lower side to take care of or to handle the renewables, right? So because of more and more renewable penetration is expanding the variation levels, boundaries. Only then we can operate. See, when you are operating fully with the conventional sources, that is synchronous generator supplying the entire power, that time the frequency was so strict. It means it is very narrow. It means 50. You can go 49.95 or you can go 50.05. Only that much level you have maintain. But now most of the grid codes are adjusted themselves. Even the frequency can go plus 2 hertz or minus 2 hertz. It means 52 to 48 hertz I can operate because of the highly random nature of renewable. So all the grid codes are adjusted, relaxed, right, to handle the renewables, right? See, the carbon dioxide emission and other environmental issues are definitely you have to take care, right? You have to address. To make up there, we are relaxed in the grid code also. You can see, you just search in the Internet Explorer, you will find that 10 years before what was the change in frequency allowed, and now what is the frequency change allowed, right? You will see the drastic change, right? It means earlier it was like less than less than 1%. Now even it is reaching more than that, right? Okay. And as a renewable service provider, right, or a renewable energy converter, when you design, you must incorporate all these ride-through techniques. It means your renewable power converters should have the low voltage ride-through, high voltage ride-through, fault ride-through. I definitely must say this, all these things. See, in conventional power plant, right, what we had 10-15 years before is something like when there is a fault in a particular point, right, the energy stored in the transmission and distribution line, also the nearby generators, conventional synchronous generators, will supply the fault current, right? So the current will come from far away places. Okay, so because of that, what will happen? The voltage will be dropped to the very low level, and it will take some time to recover, right? Restore the voltage to a normal voltage, even if the fault is clear, right? This was the case. But now the recent grid codes are saying, see, if the fault is in your premises, close to your premises or close to your place, anyway, the source, the grid, the conventional sources will supply the fault current. What the grid code is saying, you also should support the fault current, so that the amount of current drawn from the entire, earlier it was something like the entire current was supplied by the conventional generators. But now, as per recent grid code, you also should contribute the fault current. It means the fault is very close to your point, you stop your active power injection and you start to increase the current, right? For a short time, even you can increase the current beyond your rating of your inverter. Maybe 120% you can supply, something like that, right? So you have to supply the fault current throughout the fault clearing period, right? So what will happen, since you are contributing the fault current locally, the entire fault current need not come from the faraway places. So the recovery, the restoring time is somewhat faster, somewhat quick, right? So all these ways you can support to the grid, right? So that you can help the grid to function smoothly. Okay. So all these are the important points. When you connect the renewable sources into the grid, right? So you can say the challenges leads to the research opportunity, right? So when you have more and more challenges, definitely you need to have, or you are getting some openings, right, to do research, so that you can contribute to the what is it, the electrical field, right? Electrical engineering field. Okay. Of course, all these other things are actually conventional slides. So this is what I was talking. When we have only conventional synchronous generators, when the fault occurs, the kinetic energy stored in the rotor, big mass which is rotating with the synchronous generators, will support by releasing the kinetic energy stored in the flywheel or in the rotor, so that the rate of change of frequency is somewhat less. But now, most time rotating part, even for the windmill, you are decoupling. It means between the wind generator to the grid, your power converter is sitting. Since you are decoupling, it means you are isolating the mechanical devices from the inverter or from the grid. So there is no contribution of the inertia from the windmill. Of course, windmill is having a big rotating mass, but it cannot, because your power converter is in between. So when there's a fault, the rate of change of frequency is very high. So it may lead to the cascader failure or cascader shutdown, blackout, many things, right? So what the grid is insisting, the grid code is insisting, if you are having a grid inverter or grid tied inverter, during the frequency event, your inverter should supply some inertia, virtual inertia, by having a short time energy storage, that is your DC coupling or DC DC capacitor. Through that, you have to supply some extra active power, right? All those things, so that the rate of change of frequency will be less, right? So all those things. And this is actually California curve. See, the curve is plotted from 2012 data to 2020. So 2012 they have a this is actually their load curve, right? Something like this. But slowly, when they start to increase the rooftop solar PV panels, so the load curve is coming down. It means the power drawn from the central grid is coming down. By 2020, we can see around 8,000 megawatt of power requirement is reduced. But this is only during the peak hours, right? But peak hours means like peak hours of solar generation. But in the evening time, we can see from 4 p.m. to 6:30 or 7 p.m., this much power is increased. It is varying from somewhere around 12,000 megawatt to 24,000. See, almost 200% rise in the power requirement. So you just imagine, all the conventional synchronous generators or whatever it is cannot support or cannot take care of these things, right? The power ramp up, right? Power ramp up is very high and steep. So it is very difficult for the conventional generator to take care, right? So you need to have some mechanism, that is energy storage, right? You have to plan energy storage in a very big way, right? That's what discussed here. And this was the measurement data by me from one of the plant. You can see this is what I was talking, right? The solar generation is something like this. It is highly varying, right? It's not a smooth sinusoidal waveform or smooth waveform from 6 a.m. to 6 p.m. It is highly varying, right? This is the expanded version of that. You can see how it is varying, right? All of a sudden, from 600 kilowatt to it is coming, 400 or 200 kilowatt. So 400 kilowatt variation from one particular plant, right? All these things is creating a lot of issues to the grid operator, right? See, if the variation is like this is from one power plant. If there are hundreds of power plants like this, so 100 into this 400 kilowatt is very high. So no, conventional power plant can take care of this kind of ramp variation, right? Rate of change of active power variation. Okay. And the other issue is, the fortunate or unfortunate thing is, your solar PV inverter will supply only pure sinusoidal current with a unity power factor. But your loads are, most of the loads are non-linear, VFDs, ASDs, your UPS, right? Your LED lights, many things are non-linear load. So those non-linear devices requires non-linear current, right? So what will happen because of that? Since the solar is supplying pure sinusoidal, the entire non-linear current must be drawn from the grid. So the TSG drawn from the grid is increasing, right? This is how the harmonic will increase because the solar is supplying only pure sinusoidal current. The rest must be drawn from the grid, right? So all those things are issued. So because of the random variation, we have discussed something like how to plan, how to schedule, right? And what are the different methods to overcome the higher variation. That is called demand side management. You can suppress this peak, right, by different methods. That's what discussed here. And what are the different energy storage technologies are available? See, that is also discussed. It can be chemical, electrical, mechanical, electrochemical. This is where we have all the batteries, right? Flow batteries are very promising solution nowadays. Vanadium redox or zinc bromide. All those things are very promising. Even India itself, we have installed flow batteries. Right? In Bangalore, you can see a vanadium redox flow battery installed for 200 kilowatt hour, right? And lithium ion, I hope you must be knowing that in most of the EVs, they are using lithium ion. See, the thing is, after some cycles or some years of operation from EV, those batteries can be sold or can be given, give it to the grid operator. So, see, why they are selling the old batteries? Because the old batteries will lose its capacity. Maybe the capacity is, let us say 50 kilowatt hour. After 3 or 4 years or after considerable number of cycles, this battery may not have the entire 50 kilowatt hour. It may come to less than 50%, like less than 25 kilowatt hour. But those batteries can be given to grid operator, so they will use those batteries to store, right? When there is a high random variation, then they will use this lithium ion or kind of batteries. So here, see, we need not worry about the loss of the rating or loss of the energy density, right? We can handle because the number of the energy backup event will be somewhat less. So you can have the used old batteries for your grid support services, right? Okay. Then again, the role of energy storage in a different aspect, like generation, it will give a arbitrage, black start. Black start means something like, see, in a microgrid, not all the renewable sources can act as a black start. It means the source which can start and give the reference frequency to the other devices, right? It means if there is energy storage, the inverter and produce 50 Hz constant frequency and a good voltage. That can be taken as a reference to the other sources. It can be a solar PV, it can be a windmill, or it can be anything, right? So after blackout, it means after the loss of or after the loss of the entire power supply, who can start first and will dictate the frequency and voltage to the rest of the system. That's what actually black start, something like that. And transmission also, the participation of primary frequency control, secondary frequency control, reactive power control, all those things, right? See, if you have more and more energy storage, you need not invest much to develop or to create infrastructure for transmission line or distribution line, right? Right. See, there are two terminology used in energy storage. One is power density and other one is energy density. Power density is very important when you have transient response. It means suddenly I may need 10 megawatt, right? Your thermal power plant or something like that, or your pumped hydro plant cannot operate suddenly and give the 10 megawatt backup. But supermagnetic energy storage system, which are very fast in very high dynamic things actually. Within very low time, within few seconds, it can come to operation and supply the power whatever is required. High power supercapacitor. Supercapacitor, literally you can say its charging and discharging characteristics are something like this, right? So if you take a capacitor, it will be something like this. So discharging will be like this. You can have any amount of current, I, and when it is discharging, it will go like this. Similarly, charging, right? The charging also, see, it will start at very high current. And it will go to the negative. So it can start at very high current and slowly the current will decrease and charging current I have taken negative and discharging current I have taken as a positive. So it can charge at any high current, right? So suddenly there's a huge difference between demand and supply. Those things can be met by the supermagnetic energy storage or high super capacitors, flywheel, something like that, right? The average demand or average difference can be met by compressed energy storage. So those devices are high energy density. Sorry, energy density is something like what is the maximum energy? It means if the device can store maximum or very high energy, then it is having high energy density. But some devices cannot have high energy density. For example, capacitor cannot store very high energy, but it can supply very rapidly. It will respond very fast, right? So that is the difference between the high energy density and high power density, right? Power density, okay. And these are some characteristics of energy storage systems, right? You can see it later. I will share the slides, right? And in addition to the demand side management and energy storage, you can also do something in the the inverters, right? So inverters also can do many of these functionalities. So you can go through it, right? Right through, and other things can be planned from the inverter itself, right? This is emulated inertia control technique. This is the control. One of my research students followed this, and he produced many good papers, right? I was talking about right through, so low voltage right through or high voltage right through, right? It means maybe 10 years back, right? If the voltage in the grid goes beyond certain threshold level, for example, let us say 400 voltage system. If the voltage goes less than 360, right? The wind mill or wind generator which is connected to the system will get disconnected. There's a control in such a way. If the voltage goes beyond the 360 volt, the rated voltage is 400. If it goes beyond 360, then it will isolate. It means your generation is removed. So like this, there will be cascaded switching off of windmills. So what will happen? See, already there is a under voltage because of heavy load. If one by one the generators are leaving, so it is very difficult for the grid operator to manage. So like 2003 onwards, let us say, or actually that was not strictly followed that time, but after some time the people start to follow them, right? So when there is a under voltage, still even during the under voltage, the windmill or the solar PV inverters should be connected, ensure the connection and start to supply. It means we have to ensure the connectivity of the renewables even during the lower voltage. That's called right through. And similarly for over voltage, right? So everything is discussed here. Go through this, right? So I think, yeah, all these points, we have discussed. Okay, so maybe we can, stop here, and I will from you people. Yes, Professor. If people are having some questions, I can take that and I can discuss with them. So I'm happy that nobody is having questions. So they must have understood everything, or they have not got any idea, right? So there can be only two possibilities. Fine. Professor, can we wind up?
Yes, sir.
Okay. Professors, see if you have any query, and if you do not, or if you are having hesitation to ask now, maybe you can ask later by mail, or you can contact us so that we will help you to clarify the things. My area of research is actually smart grid control, the low voltage right through, then inertia control, virtual inertia control. Then the other main thing is actually energy storage. I'm doing some work in energy storage, hybrid energy storage especially. And also, my research is, extended to power quality improvement. So there also I'm working, and I'm guiding some students in my lab. So thank you very much for the patient listening. and organizers.
Yes, sir. Thank you, sir. Sir, on behalf of EEE Department and SP Colleges, we specially thank you, sir, for your availability in spite of your hectic schedule, sir. The way how you have dealt and the way how you have portrayed things was very nice, sir. I think the participants were benefited much. Actually, the reality of the concept, automation and microgrid, the things, the what you have shown, I think we may not available in general, sir. So all the things what you have quoted was very nice, sir. Thank you so much, sir. And for the participants, I think they were benefited much, sir. Some of the participants has asked your mail ID and your PPT also, sir.
Sure,
If
ma'am.
you allow, we will share the things, sir. Can we, sir? Can we share your details, sir?
Yes, yes, ma'am. Even I'm typing it, ma'am, so you can give it to them.
Yes, sir.
Yes, I have posted, ma'am.
Yes, sir. I will share the things and if your PPT has been shared with Sudhir sir also, we will share all the things to the participants at the end of all the sessions, sir.
Okay, ma'am, I know I used to show my, the research papers and other things. Can you all see this things actually? This is Google Scholar citation. Maybe.
Yes, sir. It is visible, sir. Yes, sir.
Yeah, you can see all these things. So these are the areas my students are working, and we have the facility to carry out the research. You can follow this if you need any help from these papers, right? Definitely, I can do that. So you can go ahead, right? You can go through this. And this is my scopus. So you can see these papers and my citation report and everything. And you can if you want any help from my papers, definitely I can help you.
It's a very nice opportunity, sir. I think everyone won't get this thing.
Thank you. Thank you.
Thank you so much, sir.
Thank you.
Dear participants, feedback link has been posted. So please submit the feedback link. It is mandatory for certificate generation. And please join the afternoon session by 1:55 p.m. And for the afternoon session, we have 25 questions quiz is going to be conducted for afternoon session. So you have to acquire marks of 60%. It's mandatory. So please make sure that be available for the afternoon session without fail. Thank you.